Hello students. Today we're going to look at an introduction to vectors and what they are. I'm a trifle sniffly, so if you hear me snurfling as I record this, you'll have to forgive me. So vectors are useful for representing quantities where direction matters as well as the magnitude or the amount of the thing. And this is best understood through some examples where they're useful. So the first example of a quantity that can be represented well with a vector is displacement. Here's what I mean by displacement. It's a change in position. Let's say I'm at some point, start, and then I move along some path and I stop. And it can be a curvy or a straight path, and I have an endpoint. So I have a start and an end. The displacement vector is a vector that goes directly from start to end. And the way we draw it, the way we represent it on the page is we represent it with an arrow. We just draw an arrow from start to end. And that is called the displacement vector. And so we're going to see that the way we represent vectors geometrically is by arrows. They have a tip, or this would be the tip over here, and they have a tail. So they go from tail to tip, and that's how we draw them. So this is my displacement vector. It goes from start to end. The length of the arrow, when you draw it, represents the magnitude of the vector. And for displacement, magnitude is going to represent how much your position changed in meters or centimeters, like that. Notice that vector does not measure the length of your path. Your path could do some sort of crazy, windy thing going all around, which might be quite long. But the displacement vector just measures, if you look at start, you look at end, the magnitude is how far your net change was. And then the direction of the arrow represents the length. Oops. Why did I write length there? Doesn't represent the length. I'm an idiot. Of course it doesn't represent the length. The direction of the arrow represents the direction. It's early in the morning. There we go. Sloppy, but it represents the direction of the vector. So displacement has two things you're keeping track of. The vector keeps track of both of them. Displacement has how far your net change in position was, which is represented by the length or the magnitude of the vector. And it also has the direction, which way I went, which is represented by the direction the arrow points. And notice that for a displacement vector, it doesn't matter what path you take. All that matters is where you start, where you end. The arrow doesn't represent the path that you took. The arrow simply represents your change from start to end in your position. So, another thing that's represented well by vectors is force. So here I've drawn my very complicated picture of some heavy block resting on a surface. And I could pull on this block with a rope or something, or I could push on it. And that pull is represented by a vector. So this arrow is going to represent a force. I'm pulling on this block. So if I change and pull a different direction, I'll get a different vector. And if I pull harder, then I would make a longer vector. So here, the magnitude represents the strength of the force, however you're measuring strength, pounds or newtons or whatever. And the direction is which way the force is being exerted. And that's why force is represented well with vectors, because it matters not only how strong you're pulling, it matters which way you're pulling, how it affects the block. Okay. A third thing that is represented well by vectors is velocity. So let's say here, again, my artistic skills are on display here. Here I have some sort of lake or something, and I have a motorboat. In fact, let's put a little motor on the end. There we go. So if I turn the motor on and point my boat in a certain direction, I get a velocity vector. So here the arrow is representing not only how fast I'm moving, but which direction I'm moving. If I turn the boat to a different direction, I get a different vector because I'm now moving in a different direction. And if I turn up the motor so the boat goes faster, then I would get a longer vector. So here magnitude represents the speed in miles per hour. The direction represents which way I'm traveling. So all of these things are represented well with vectors, and we'll see why as we go through this unit. So now we need to talk about combining or adding vectors. We're going to do this again in another later lesson, more precisely when we do it with components. But now we're just talking about just drawing pictures, adding them geometrically. There are two common methods. They amount to the same thing. Okay. One method for adding vectors is called the tip-to-tail method, which is really good when you're working with displacements. So let's imagine we have some path with a start and an end, and we have a displacement vector. So there's my displacement vector. But then, from this point, now I'm going to continue my walk, whatever I'm doing. So I follow a second path, and now I draw another displacement vector from there to there. So what is my net displacement? Well, I started here and followed some long, complicated path and ended up here. So my start was here, my end was here. So my net displacement, my final displacement after doing all that, is a vector that goes like so. And this gives the idea behind tip-to-tail method for adding vectors. So let's say I have a vector that I'm going to label u. Typically when we're working with vectors, we use the letters u, v, and w. And I have another vector that I'm going to label v, and I want to combine them or add them. So what I do is I take a copy of u, and then at the tail of u, I put a copy of v, the tip of v, it's going to go that way because it's going to be a copy of v. So I put v like that. So I've taken a copy of u, put it there, and then I've taken a copy of v, and done it tip to tail. Then to combine those vectors, I just go from where I started, the tail of u, to the tip of v. And that's called tip to tail adding. We call that u plus v. So there's something to note here, and that's, before I go on, and that's, vectors can be moved around in the plane to work with them. They're not attached to a particular position. Just like numbers, you can write numbers in different places on the page to work with them. You can take your vectors and move them around in order to perform these different operations with them. It's okay. All that matters is you keep the same length in the same direction when you're copying them around. So there's one reasonable question is, why do we call this adding vectors? And there's a lot of reasons we call this adding vectors, but one is that it doesn't matter which way we add. If I were to reverse this and do v plus u, then that would mean I would get something like this. I would take v, make a copy of it there, and then from the tip of v, I'd put the tail of u, put it there, and then I go tail of v to tip of u, and that's v plus u. But if I look at v plus u and put it over here next to u plus v, they have exactly the same length and direction. They're the same vector. So u plus v is exactly the same thing as v plus u, which is, if we're going to call it adding, we would expect it to behave that way. That's one of many reasons why this is called adding vectors. This is one method for adding vectors. It's really good for displacement. It's also really good if you have to add a lot of vectors up. Let's say I've got three vectors, u, v, and w. I want to add them all together. So I just pick one, and I think I picked w here, and then I put a copy of v on the tip of w, and then I went from end of to v, and put a copy of u. So I've got w plus v plus vu, and then So if I go from the very beginning to the very end, I get the sum of the three vectors, u plus v plus w. And that's a perfectly good way of acting vectors. There's another way, which amounts to the same thing. They don't give different answers. You could use either one, but both methods are useful for certain situations when you're trying to visualize things in a certain way, because in certain situations it's more useful to think of all the vectors having the same tail, particularly when you're dealing with forces. Let me show you what I mean. So let's go back to my block here. So there's my block, and I'm going to have two forces acting on it. So there's going to be my first force, which is going to be, you can think of it as a rope or a magnet or a push or something that's pulling on that block. Remember, the length is how strong the force is here. So this is a fairly strong force pulling up this way. And the direction, of course, is which way the force is pulling. Then I have another force pulling off to the side. And I've labeled them F1 and F2 since they're forces. So let's say I want to combine these forces. I've got these two forces. Here's force 1, here's force 2. And I want to add them together to see what the net force is. How strong and which direction are these two? If we combine these forces, how strong will the combined force be? So notice I already have them drawn sharing tails now. So this is not tip to tail adding. We're going to go like this and then go like this. But you'll see it amounts to the same exact thing. So what I do for the parallelogram method for adding vectors is I have them tail to tail like this, like I'm pulling on this block, and so I put both forces with the same tail. And then I think of these two forces as two sides of a parallelogram, and then I put in the other two sides like that. So there I have a parallelogram. The sum of the vectors goes across the parallelogram from the tails across to the other side. So that's going to be F1 plus F2 here. And notice that this is the same as tip to tail adding, because here's F1 and then F2 goes like this. Or here's F2 and then F1 goes like this. It's just a different way of visualizing the addition that's particularly good when you're working with forces, when you have all of these arrows pulling from the same place on the block. One more thing. We need to understand what it means to multiply a vector by a number. So let's say I have a vector u. What might 2u mean geometrically? And you probably have a pretty good guess what 2u might mean. But let's see. If what we're doing makes any sense whatsoever, then 2u should be the same as u plus u. And it is. 2u is u plus u. And we know how to do u plus u. You just do u, and then you add another copy of it to the end. And then, so this resulting vector is what's represented by, is what's called 2u. So it just doubles the length of u. It goes all the way from there to there, leaving the direction unchanged. And that motivates my definition of multiplying a vector by a number. When I do k times u, if k is a number, then I multiply the magnitude or the length of the vector by k, and I leave the direction alone. It's left unchanged. So if I have some vector v, then 3v would look like that. Same direction, but 3 times as long. 1/2 v would look like that. Same direction, half as long. But wait a second. What about minus 2v? Can I multiply a vector by a negative number? And the way we define this is I have to go back and change what I wrote up here. We can multiply a vector by a negative number. What we do is we say, well, if I'm going to multiply by a positive number, I leave the direction unchanged. But if I multiply by a negative number, I reverse the direction. So it points the opposite direction. So minus 2v would be a vector twice as long as v, but pointing in the opposite direction. So minus 2v would look like that. There it is. It's twice as long as v, pointing in the opposite direction. So let's us now, instead of adding vectors, let's us subtract or do different ways of combining multiples of vectors. So if I wanted to do u minus v, I take a copy of u, and I take v, and minus v is minus 1v. I'm just going to reverse its direction, leaving its length alone. So I'm going to turn it around. So I scratched off and put an arrow on the other end. So there's minus v, and then u minus v. I'm going to do tip to tail adding. So I have tail of u to tip, and then I have tail of v minus v to tip, and there's u minus v. One last thing. There's a peculiarity with vectors. What's u minus u? Well, 0, I would guess, but what is it? Is it a vector still? We've got u, and then we've got minus u, so we go there and back again. It's like the Hobbit. And so we end up back where we started. Is this a vector? Well, if we add two vectors, we should get a vector. Is that a vector? And what we need something that represents 0 when we're working with vectors. And so we just define it. We say, okay, well, u minus u is going to be the 0 vector. And we put a little bar over the 0 to distinguish it from the number 0. What the heck is a 0 vector? Well, it's a vector with magnitude 0. I don't know what direction it goes because it doesn't go anywhere. It doesn't really make any sense to say which direction the 0 vector goes. But it's a vector with magnitude 0. It's hard to draw. I mean, it's a point, right? But we define it to be a vector with magnitude 0 and indeterminate direction. It doesn't make any sense to talk about direction. But I want to make sure that you'd seen that so you weren't confused if you saw it in the future. And that ends the lesson. So you should be ready to look at the handout. Thanks for listening.